Hi, this is Bob Rasooli from Orange County, California, and in this session, I'm going to walk you through a challenging API 571 exam-style question focused on naphthenic acid corrosion, section 346, using the vacuum tower region highlighted in the following PFD. During inspection of a vacuum tower wash section and the heavy vacuum gas oil, HVGO draw zone, the unit was processing a high total acid number, TAN crude blend. Internal visual inspection reveals localized crescent-shaped grooves and noticeable thinning on the shell just below a high-velocity HVGO draw nozzle. The metal loss is aligned with the direction of liquid flow, and it is most severe where hot liquid drops and splashes against the shell. Process data confirm that this circuit operates at typical vacuum column hot oil temperatures with no free water phase present, while the sulfur content of the feed remains moderate to high. Downstream light vacuum gas oil (HVGO) circuits show very minimal corrosion. Which of the following mechanisms best explains the observed damage in this part of the vacuum tower? Option A, high-temperature sulfidation of carbon steel promoted by elevated sulfur content and typical vacuum column temperatures in the wash section. Option B, naphthenic acid corrosion causing localized, flow-oriented metal loss in the high-velocity, hot hydrocarbon region near the HVGO draw, where naphthenic acids are concentrated. Option C, hydrochloric acid, HCl, corrosion caused by condensation of acid droplets in the wash section as overhead vapors cool and form an aqueous salt solution on the shell. Option D, erosion corrosion from entrained solids in the HVGO draw, where particulate-laden droplets impinge on the shell, causing purely mechanical wear unrelated to fluid chemistry. Sulfidation is definitely a major concern in crude and vacuum units, and it does correlate with high sulfur content and elevated temperature. However, sulfidation typically produces generalized wall thinning across a broader area rather than the sharply localized directional grooves described here. The pattern in the scenario is clearly defined by flow direction and velocity, which sulfidation alone does not explain. In addition, sulfidation in vacuum towers more commonly affects heater coils, transfer lines, or lower wetted sections with uniform temperature profiles. It does not selectively attack just below a high-velocity draw nozzle, nor does it typically produce the crescent-shaped wipe marks that are strongly characteristic of a velocity-dependent mechanism like naphthenic acid corrosion, or NAC. Therefore, option A is not the best explanation for the observed damage. Option B, naphthenic acid corrosion or NAC. Naphthenic acid corrosion occurs in high-temperature, water-free hydrocarbon environments where naturally occurring naphthenic acids in the crude oil aggressively attack carbon steel. Naphthenic acid corrosion, NAC, becomes especially severe where velocity and wall shear stress are high, such as side draw nozzles, pump suctions, transfer lines, and splash zones. The damage described, flow-oriented grooves and crescent-shaped thinning in a hot, water-free, heavy vacuum gas oil, HVGO region, is textbook NAC morphology. This is further supported by the use of a high total acid number, TAN crude blend, which concentrates naphthenic acids in heavier fractions such as heavy vacuum gas oil. Naphthenic acid corrosion is well known to be unevenly distributed in vacuum towers, often severe in HVGO regions, while lighter vacuum gas oil, LVGO, remains mostly unaffected, exactly as stated in the scenario. Taken together, the temperature, total acid number level, velocity, location, and type of metal loss align perfectly with naphthenic acid corrosion, NAC. This makes option B the correct answer. Option C, hydrochloric acid corrosion. Hydrochloric acid corrosion requires water condensation because HCl must be in an aqueous phase to attack steel. This mechanism is therefore associated with cold-wet overhead systems, ejector circuits, and condensing sections, not with the hot, dry hydrocarbon interior of a vacuum tower wash section. The scenario specifically states no free water phase, which immediately excludes HCl-driven corrosion. Additionally, HCl corrosion generally produces a more uniform pitted pattern in cold-wet regions and has nothing to do with high-velocity liquid flow, splash zones, or TAN content. The localized grooving and flow orientation described here have no relation to aqueous chlorine salts or overhead condensation. For these reasons, option C cannot be correct. Option D, erosion corrosion. Erosion corrosion can indeed result in directional metal loss, especially when solids, coke particles, or catalyst fines are present. However, nothing in the scenario suggests entrained solids, particulate load, or mechanical abrasion. The emphasis instead is placed on high TAN, high temperature, no water, and intense flow-oriented grooving, all of which point toward a chemical corrosion mechanism, not mechanical wear. Furthermore, naphthenic acid corrosion itself behaves like a chemical erosion hybrid, where velocity accelerates the removal of protective layers. Mistaking NaC for pure erosion corrosion would ignore the critical role of acid chemistry. Since no evidence of solids is provided and the environmental conditions perfectly match NaC, option D is not the correct answer. Final conclusion? Only option B, naphthenic acid corrosion, explains the full combination of high TAN crude, hot, dry hydrocarbon service, high velocity at the heavy vacuum gas oil, HVGO draw, and the distinct flow-oriented grooves observed in the vacuum tower.